Okay. So, right. So, whatever questions you've got, break it on. Unless you're
Wait,
all
did you ask? We had questions.
Yes.
Okay. On point 1.2.28.
Okay. Wait. During a previous class where you can tell me a problem number, and I start scrambling to get the PDF of the book open, then I realized, oh, duh, I got it right here.
I don't know why.
Sorry, what?
I keep echoing.
I know. That crap needs to stop. It's weird how intermittent. Okay. Okay, the sum function.
Yeah. So I was able to compute the sum of a matrix, but I was confused by the question, how can you get sum to produce the opposite of this default behavior? I wasn't sure what you meant by opposite.
Okay. All right, so I know I'm going to at least partially give a question away, but I'm okay with that. To everyone else, but when you took sum of a matrix, what did it do? Like what result that it gave you? What was it?
The sum of each column in a row vector.
Okay. So all right, I'll put this. Okay, so the sum of each column is a row vector.
Mm-hmm.
So this is for all four of you. Can anyone suggest what an opposite of that kind of result would be? Like, well,
we would want the sum in a column.
Yes. That's the behavior. That's what my opposite.
I'm sorry, I didn't hear her.
Okay. Yeah, I didn't hear entirely either, but I kind of filled in the blanks. But go ahead, try again, Walker.
I was saying we want the sum of whatever of the row vectors in a column vector.
Okay. Yeah. The sum of the rows. That's a column vector.
Yeah. I'm echoing.
Okay. Chelsea, did that come through from either one of us?
Yeah, I got it.
Okay. All right. Yeah. Well, with this audio, you never know. Okay. And the thing is, there's no obvious way, because what you're doing with your matrix A, you're doing sum of A, and this is what you get. So yeah. So really, this is a problem all about consult the documentation, because it's something I want to get you all accustomed to doing.
I had one for 1.2.17.
Okay.
I already talked to you about why it was 0.00 or negative 0.000, but as for the why, am I supposed to be finding something within the math or the code as to why that's happening?
No, it's just I'm asking you to speculate.
Okay.
Because honestly, it's something that gets covered in more detail than in the next chapter. So.
Okay.
not remembering, I think I was in high school or something when I got a question like that, because the way it's worded, it says, can you explain why, blah, 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 blah. And I simply answered, yes. Teacher wasn't very happy about that. Like, okay. All right. Anyone else need to chime in on about any of these? Or if you have more, Chelsea, of course, you can. Okay. Okay. I want to make a preemptive comment about one that I imagine all four of you would appreciate, whether you've gotten to this problem or not. The last one, number 29, where the user type specifies a date, month, day, year, and the code returns the day of a week for that date. And the thing is, this is going to piggyback off of number 14. So what do you have from number 14, where it determines the number of the day within the year is literally that's how this function would start. That you get the input date, and having the number of a day within the year is part of what you need. It's just that you're going to add some things to it. And what I would recommend is, just to get ideas to how you get from this date that they've given, and also therefore a day within a year, so you can jump to that point directly based on your number 14 code. How do you get from that to an indication of day of a week, like 1 through 7, from Sunday through Saturday, or even 0 through 6, Sunday through Saturday, because it's a remainder after dividing something by 7. Try working with sample dates. Like, for example, suppose now there's a reference date given that December 31st, 1999 is a Friday, or was a Friday, and the way you so then as a simpler case, it's a good idea to start with simple cases. Like, what if a given date was in the year 2000? So that would be the day within the year. You would work with that and go from that to a day of a week. Then if you have a date during a different year, then you have full years to take into account. But you can handle this problem a piece at a time. And this is how a lot of algorithms in numerical analysis are designed, that we first handle some particularly simple cases, if that applies. I'll work that out first, and then generalize from there. So it helps make the task a little less monstrous. And there's always things that can be done to break it down a little bit, and set certain concerns aside. And I really think that there's a psychological benefit to that, because let's suppose you do figure out, okay, here's how you handle a date given of the year 2000. Then, okay, it's like, so that part, you've handled it. And then that gives you some strength to take on the next part of it. I found out to be quite helpful when taking on larger things. And you've probably found that just to be true just in general, that if you have some monumental, overwhelming task and you find it's really getting to you, anything you can do to break off a piece of it and handle it, it gives you a boost. beyond just getting a thing done by itself. So, but yeah, this one's nasty. So, then hope you like it, then something you can definitely feel good about. But also, definitely no shame if you don't. So, don't want to keep that in mind. But definitely feel free to send questions my way, whether it's in here or outside of class. If you get stuck on that one, especially. Okay. Of course, the date, December 31st, 1999, makes me think of something that was going on when all four of you were extremely young, and that was Y2K. So y'all would have been like, I don't know, maybe 3 or 4 years old around that time. So I don't know if if you were ever acquainted with all the pretty much kind of hysteria that was going on around that time, 1998, 1999, concern about how flipping over to 2000 would, cause some sort of disaster because of concern about, if dates are represented using a 2-digit year, and then so 98, 99 flips over to 00, and what chaos may ensue. And a lot was done about it at the corporate level, like ensuring Y2K compliance, and a lot of companies try to make money off of it to to ensure that companies were compliant. And the funny thing is, when all this was unfolding, there was a lot of talk about it, but I actually had a feeling that it was going to turn out to be nothing, that it wasn't going to be a big deal when we switched over to 2000. And the reason why I felt that was because I knew about how dates were represented in software. Like, if you're using whatever programming language and you're working with dates and times, and you're just using whatever standard functionality, like you're not trying to build it all yourself, you're using what's already there. Well, those did not represent dates using 2-digit years. Dates are actually represented using, like, for example, the number of milliseconds since January 1st, 1970, or something like that. So flipping over from 1999 to 2000 would make no difference whatsoever. So while everybody was all up in arms about it, I'm like, you know what? I think it's going to be a dud. I don't think anything's really going to come of this because the way we represent dates is not sensitive to that. And yeah, a few comical things did happen, like someone got a bill for like $100,000 for a late video, but other than that, it was like nothing. So, but this goes to show that how you represent your data makes a big difference. Like I've talked about how numbers are represented, using a certain number of binary digits and also an exponent. And what if a representation that seems perfectly fine now should change? And with dates, you have to be very careful about that. It's something that makes up, there's a lot more that goes into it than one might think, because these things have to last for a while. Okay. Okay, first, in the meantime, has any other questions come to light before I talk about something else? All right. So what I want to do is, since next week I'm going to get big into polynomials and how we approximate functions with polynomials. I want to show you some things in MATLAB. So again, certain helpful MATLAB tasks in demonstrating this, but also setting a stage for that topic when we get into Chapter 7. And I promise that any other assignment I give you for the rest of the semester will not have 29 problems. That's an outlier. Okay. So now I'll get my MATLAB shared. Okay. And I'll get a diary going. All right. Okay. This text that you see me type in the MATLAB window, is it a good size? Like, is it readable enough? Because I made it a little bigger than what I normally do, but didn't want it too big. Okay. So, the problem that I'm going to start covering in detail next week is called polynomial interpolation. So I'm going to describe the problem, and then I'll show you how it's handled in MATLAB, and then do some examples of interest. Okay. Or at least I find them interesting. Hopefully you will too. Now, here's what you're given. You're given a set of points in the plane, so x and y values. And they're numbered from 0 up to n. And we're going to assume that all of the x's are distinct. That's not necessarily a given, but we do need that assumption here. Okay. So we're given n plus 1 points in the plane. Find a polynomial that I'll call Pn of x. And I call it n, Pn, because it's of degree n, that passes through all these points. So if I plug in an x value, I will get the corresponding y value. All right. So now a simpler version of this problem you've been solving for several years, like given 2 points, what's the equation of a line between them? So now we'll generalize this, because in that case, you figure out the slope and like use point slope form to write down the equation. So by next week, what you'll be able to do is if you're given any number of points, so n plus 1 points, you'll be able to write down the formula for the polynomial that passes through them. So great thing to do at parties. Now, so how does MATLAB solve this problem? Now, we're going to treat this as a black box. It won't be until next week that I really get into the method of how it comes up with it. And like how this MATLAB function does its job. But for now, here's the function, polyfit. Okay. So what you do is you have a vector of your x values. You have a vector of your y values. And then you specify the degree. Now, for this case, the degree should always be 1 less than the number of points you have for what we're talking about here. Otherwise, it'll come up with some other approximation. And then what it gives you is P. P is a vector of coefficients of a polynomial, which you've been working with a little bit on the homework. Coefficients ordered from highest degree to lowest. And then you can use that with other MATLAB functions that deal with polynomials. Okay. So what I'm going to do is, so as an example, I want to find a quadratic approximation of e to the x using the points x equals 0, 1/2, and 1. So 3 points, that'll give me a quadratic. Just as 2 points gives you a line. Okay. So to do this in MATLAB, I'll define my vector of x values. So 0, 1/2, and 1. And then I want my y values. So that'll be, I'll just take exp of my x values. Okay, I want to make sure I'm not getting super long numbers here. Now, I will do polyfit. So I have x, y, and then the degree will be 2. And let's see what we get. Okay, so these are the coefficients of my quadratic function that approximates e to the x. And so it's 0.8. So I'll write it down here. So P2 of x is equal to 8417 x squared plus 8766 x plus 1. And it makes sense that this coefficient will be 1 because if I plug in x equals 0, 1 is what I'll get, and that's e to the 0. So certainly those should agree. All right. So now what I want to do is I want to plot my polynomial and also e to the x. Now, all right, so my polynomial is p, so I want to plot this on the interval 0 to 1. Now, I could just say plot x and y. In fact, I'm going to do that right now to show you why it's a terrible idea. If I do plot x, y, come on. Why is it slow? Okay. All right. This does not look right. This definitely doesn't look like e to the x. Doesn't look like a quadratic function either. Why? I only have 3 points. So it's just playing connect the dots. So that's not going to help me. Because I want to be able to compare these two. So let's dispense with that. We need a lot of x values. Now, this is something that comes up in the homework for 2 functions, graph poly and graph func. So I'm going to make another vector of x values. I'll call it xx because I don't want to overwrite x. I'll use linspace. And I want points between 0 and 1. So that'll give me 100 equally spaced points. So this is the default usage of linspace. So then I want to plot the exponential. So I'll plug those into exp. And I'll call that yy1. And then I also want to evaluate my polynomial at these same points. So I'll polyval of p, and then I plug in my x values, xx. So yy1 is e to the x, yy2 is my polynomial, my quadratic polynomial. Now these I will plot. So I'll plot this in blue, and the default is blue, but I want to specify it explicitly anyway. Okay, there, at least it's a curve. I mean, it's really, 100 points and play connect the dots, but with this resolution, it looks like a smooth curve. Okay, then I'll hold on, and I'll plot my polynomial in red. And what we can see, if you look closely, they don't agree exactly, but it's pretty close. This is a good approximation. Then what I'll do is I want to plot my data points, my 3 data points, and I can use black circles. So K is black, and O is for circle. And we can see the 3 points at which they agree. So you can kind of tell that there's some deviation in between, but then they come back together at these points. So the error is always 0 at these interpolation points, and it's non-zero in between. Okay. I also want to show you some annotation. I'm going to do X label X, Y label Y. One of the homework problems just came up to label your axes. So something you definitely want to do when you're including a figure in a paper or presentation. Okay. And also legend. The first curve I plotted was the exponential. Actually, I'll do it right this way, e to the x. And the second curve I plotted was my polynomial. So I'll do p underscore 2 of x. So that'll give me a nice legend. Okay. Where'd it go? Oh, there it is. Okay. All right. I don't know how well you can see this. I'm going to see if I can make it bigger. Because notice, I don't like where it put the legend. It put it on top of your curves. It's really annoying that way. It always finds a way to do that. Like it's trying to undermine you. But what I did here, watch what I did. I clicked on the arrow at the top. And that allows me to select items. So I click here, and then then I select this. Now I can make it bigger just by dragging. Okay. And actually, I don't know how well you can see this, so I'm going to make the text bigger. So here's something else for presentations that's very important. I hope I didn't show this already, but in any case, if I go here to preferences, now I'm on a Mac, it might be different on Windows. If I go to preferences, okay, and I select figure copy template, and notice there's settings for documents or presentations. The default is documents. I'm going to pick presentations. And then it says apply to figure. And I'll show you what it does. All right. Notice everything's a lot more visible now. The text is larger, the text is bold, the curves are thicker. The reason for this is how the figure appeared before is generally fine if you're going to save this as an image file and put it in a document. But if you're going to give a presentation that has to be shown on a screen, like through a projector, you want to do this instead, so that it'll be visible on screen. So that's why MATLAB put these settings in here. Now, the other thing I want to point out, look at e to the x and p2 of x. What I typed, I'll put that back up, was e arrow x and then p underscore 2 of x. It interpreted those as superscripts and subscripts. So when you make text labels like this, there's a very primitive LaTeX interpreter that will let you type in expressions like this. or like it'll understand Greek letters, things like that. So that's helpful for annotating these things. Now, also, I don't like the legend being on top of my curve, so I can move it wherever I want. Okay. All right. Now, I'm going to save this so I can upload it later. Now, very important point when saving figures. Okay, so I'm going to do save as here. Come on. Okay. Now, the default is to save it as a .fig file. So I'll go ahead and do that. And then I'm going to save it again. I mean, notice how slow this is. And there's several image formats you can choose from, like JPEGs, Windows bitmaps, things like that. I'm going to choose PNG, that's portable network graphic. So it'll be insert PNG. Now, watch closely when I hit save. Watch what happens. I'm serious, if you blink, you miss it. I hit save. And, okay, notice it flashed white for a little bit. Now, my computer's running slow today, so usually it's a lot faster than that. That's when it's actually saving the figure. So don't close it until you've seen it flash. Now, I saved it in two formats. Image, so you take the image and you put that in your document, but also the fig, always. Right, so for plots, always save as a .fig, not GIF, fig. Why? Because if I close this now, and I'll click on here to reopen it. So like if you close down your MATLAB session, you can get it, you can come back to this later. Now, suppose I put it in my document and then I find like, you know what? I don't like the way it looks. I want to change some things about it. Maybe change some text labels, that kind of thing. Maybe put a title here. If it's a .fig, you can go back and do that. You don't have to rerun what I did here to create this. You can just mess with the .fig. If you only save it as an image file, and then you got to make changes, you're SOL. Okay. So this is something that served me well with working with figures and putting them in documents and presentations and all that sort of thing. Okay. Questions so far about getting a polynomial fit and also plotting it?
Yeah, just I need to repeat. What did you do with the preferences again?
Wait, with what?
I'm echoing. What did you do with the preference thing? Can you do that one more time?
Yeah. Okay. So figure copy template is where you go. And then I clicked on presentations. Like I can, like here, the default setting is to not do anything. Presentations will have these settings, which you can customize, like making a text bigger, making it bold, making lines thicker, that sort of thing. And then I hit apply to figure to actually make it take effect.
Thank you.
Yep. Okay. All right, now I'm going to show another example working with a different function. So my function is 1 over 1 plus x squared on the interval -5 to 5. Okay. So for my x values, well, first I'm going to define my function f using a function handle, because this is too simple a function to create an M file for. So I have f of x will be 1 over 1 plus x squared. Now, Notice the dots. 1 dot divide, 1 plus x dot squared. I want the function to be vectorized. If I plug in a vector for x, I still want it to work. You cannot divide by a vector. You cannot square a vector unless you put the dot in these operations. So now I can plug a number or vector or matrix into x, and it'll take 1 over 1 plus x squared at each element. All right. So that's how you create a function handle. You specify @, what the arguments will be, as many as you want, and then the formula. So these are like quick on-the-fly functions. Good for testing things. Okay. Now, I want to approximate this function on -5 to 5. By x values, I'll use the integers from -5 to 5. So total of 11 points. 11 points will give me a degree 10 polynomial. So my y values, I'll plug them into f. All right, so now I have my data to interpolate with. And then I'm going to get my interpolating polynomial. So x, y, and 10. Okay. So this polynomial will agree with f of x at these points from -5 to 5. So now what I want to do is I want to graph both of these again, like I did last time. So I'll do the same thing as before. I want a vector of values, equally spaced values, many of them, between -5 and 5. So this is just for plotting purposes. Okay. So then what I'll do is, like before, I will plug them into my function and also into my polynomial. And now I can plot. So first the function. So this is 1 over 1 plus x squared. And it behaves like you'd expect that as x increases in either direction, the function is going to 0. When x is 0, it's equal to 1. It's a nice smooth curve. Now on top of this, I'm going to plot the polynomial. I'll do a hold on, and then x, y, y2 in red. And things didn't go so well. So this polynomial is a terrible approximation of its function. It's pretty good around here, near x equals 0, but once you move away from it, that's awful. So, but now I'm going to plot my 11 points in black circles like I did before. Notice they still agree. The polynomial did what it was designed to do. It matched the graph of f at these 11 points. And elsewhere did not even come close. So polynomial interpolation is something you have to be careful with. Do not assume that just because your polynomial agrees with a given function at selected points, that's going to be anywhere near that function in between. So we will study interpolation error at some point, not next week, but like the week after probably. And so what will happen then is we'll see how the error can get extremely large. Now, so as for why this is such a bad approximation, take a look at f of x, the blue curve. It's pretty smooth. But here you have a polynomial of degree 10. A polynomial of degree 10 can have as many as 10 roots. What does that mean? It's probably going to oscillate. So the higher degree of polynomial, the more oscillatory it's going to get. The function you're trying to fit is not oscillatory at all, really. So, so there's a disconnect there in behavior. You might be better off trying to fit this with a lower degree approximation, and that would actually turn out better. So with high degree, you need to be careful. So most often when people try to fit functions with a polynomial, if a function you're trying to fit is pretty smooth, go with something of low degree. Like probably no higher than cubic. But high degree in and of itself is not a deal breaker. So what I'm going to do is I'm going to fit this function again with the same degree. I'm going to still have 11 points to fit of a degree 10 polynomial, but I'm going to use different x values. Now, I want to do this in a separate figure. So notice it says figure 1 up here. I'm going to do this, figure 2. So now I have a new figure window to plot in. So I'm going to show you how I get better points, better x values to work with. And I'm going to do that using the unit circle. So what I will do is I'm going to define a vector of angles using linspace again. I want angles from 0 to pi, equally spaced. Okay. And then I want to plot cosine of t and sine t. I want points on the unit circle. I only went from 0 to pi, not 2 pi. I only want the upper half. So now if I go to figure 2, there's my circle that is very much not to scale. Let's fix that. Okay, that looks better. Okay. Well, now I'd like the whole thing bigger, but still to scale. Okay. So now I have my half circle. What I want to do now is I want to have equally spaced points on the circles. In other words, equal spacing, not in X or Y, but equal spacing in the angle theta. Okay. So I'm going to create a vector of 11 equally spaced theta values that lie on the circle. Okay. Actually, I don't need this t anymore. I shouldn't have called it t. I'm going to override it with this t. So I'm going to take. I want to make sure I get these angles right. This is what I get for not really preparing this example. So hopefully this doesn't go wrong. But you know, those of you who are teaching, well, then actually all of you certainly will teach if you're not already. This might be a cautionary tale for you. Okay, but since I didn't prepare this, I'm going to go very slow. Now, I want to take the indices 0 through 10. And I want equally spaced angles in here, but I don't want to include the endpoints. So if I do this, 2 times 0 to 10 plus 1. So the maximum value of this will be 21. So I'm going to divide by 22. So this will give me 1 over 22, 3 over 22, and so on, all the way up to 21 over 22. All of those numbers are strictly between 0 and 1 and are equally spaced. But then I got to multiply all that by pi. So those will be my equally spaced angles. Okay. Now I'll do a hold on, and I want to plot those points on the unit circle using red circles. Okay, and sure enough, that looks like how I hoped. Okay. So now to get my x values, what I'm going to do is I'm going to take these points and draw a vertical down to the x-axis. So I'll show you what that looks like. Okay, so first I'm going to plot them on the x-axis. So same x values, but y equals 0 for the x-axis. So now you can see them there. And it's hard to tell, but these actually line up. So to show you that, I'm going to do a for loop. So I have 11 points. So I'm going to loop from 1 to 11. And I'm going to plot a line going from the x-axis up to here. So my x value will be cosine t of I. In both cases, same x value for a vertical line. Y value goes from 0 up to sine of that same angle. Now use a red dashed line. Then I end the loop. Please let that not screw up. Okay, so for a totally winged example, this worked out really well. So notice I took these angles are equally spaced. But then when I take the corresponding x values by taking cosine of those angles, notice the x values are not equally spaced. They're congregated around the boundary. So what the hope is that by using points with greater concentration near the boundaries, notice in the upper figure, look where the large error was at the boundaries. So by clustering points there, the hope is that this will reduce the error. So let's try that. X is equal to cosine t. So new x values. These are called the Chebyshev points. I'll go more into them more detail like next week. But the idea is you take equally spaced angles, then take their cosine to get the x's. So they're not equally spaced in x, only theta. Okay. Then my y values will be f of x again. And now my new polynomial, I'll use polyfit with these x values. Still degree 10. And now I want to go back to this figure, and I want to plot that same polynomial. So I need more y values. I need polyval with this polynomial and my previous x values that I use for plotting purposes. And now I can plot that polynomial. So I want to go back to figure 1 to make sure I'm using this figure now to put all these graphs in the same plot. So when I do plot xx, yy3, and see I have blue and red. I'm going to use magenta. So M. I could use cyan or yellow, but that might not come through well over the connection. Okay, there we go. Ah, what happened? Okay, this is okay. Something's super wrong here. Oh, I know why. No problem. I knew my lack of preparedness would bite me sometime. Okay. Thankfully, what I just did is easily fixed. Let's take a look at the x values. They're all between -1 and 1. What x values am I supposed to use? Between what range? Look here. Anyone?
-5.
Yeah, -5 to 5. So I need to scale that. So x needs to be -5, not minus 5 times x. Okay, so now let's just repeat. All right. Whew. Okay. So I need to redo my y values. I need to redo my polyfit and my graphing y values. Okay. But at least I was able to go back and just delete that bad curve. So let's try this again. Okay. All right. Here we are. Okay, let me make this bigger. All right, so look at this magenta curve. It fits the blue curve at different points, but notice it's still not great. There's still some error here, but it's a much better fit than what we had before. So having equally spaced points and high degree is generally a recipe for trouble when you're trying to fit a function to a polynomial. This alternative of using a Chebyshev points makes things a whole lot better. Now, it's intuitively we can see why, because before the error was at the worst at the boundaries, and now we have points clustered near the boundaries to give more attention where it's needed. But there's still more to it than that. And once we see what the error is in the interpolating polynomial, I'll be able to show you in terms of that why Chebyshev is a good choice. Okay. Right, so questions about anything that happened here? And I'll post a diary and figures in Canvas later, but or any last MATLAB questions of any kind before I let you out early.
Already. Oh my gosh.
What?
So much echo. I sort of already asked this, but there's a lot of IM files that we create. Are we turning in all of them?
Yeah.
Okay, just making sure. I didn't want to like spam you with like 10 IM files that you didn't want.
Oh, nope, spam away.
Okay, sounds good.
All right. Oh,
Yeah, on that note, you said you've had, I don't know, especially a lot of my earlier assignments. There's just lots of mistakes. You said that doesn't bug you to turn in, or would you like us to like erase a lot of those within the?
Oh, I see. As long as I can navigate.
Okay.
Like I want to look at. Okay, here's your work problem 1. Here's your work problem 2, and so forth. So
Yeah. I have to change from the beginning because I don't know if I was commenting or doing anything at the very beginning, but yeah.
Okay.
But by the end, it's a lot better.
Okay, well, that's good. I'll keep that in mind. Any other? I'll make sure to save these.
I noticed you just turned your diary off. Are we supposed to do that whenever we finish?
Well, if you shut down your MATLAB session, that'll do it too.
Oh, okay. Just curious.
Yep. Any remaining questions? Alrighty. Well, good luck wrapping up MATLAB. And I'll be looking forward to seeing what you all turn in. And we'll dive into polynomial interpolation next week. So I'll get this recording off. So yes, I'm letting it go so early because I'm sure we're all exhausted. So, okay.